In this video, I'm going to work through a few challenging exam questions from the energy topic of AQA GCSE physics. Have a read of this question. It's numbered question 7 because it was taken from a set of questions where the first 6 were a lot easier. Have a read of this question. If you've not done it before, please do it now. Pause the video while you do it and press play once you have completed the question. I'm now going to go through this question step by step. While I do that, I'm going to be asking you several questions. Whenever I ask you a question, please answer it to your video. So we start with question 7a. We need to draw a label diagram to show how specific heat capacity can be measured. So to do that, you firstly need to draw your cylinder of aluminium. The diagram does not need to be good, but it does need to be labeled. So I'm going to label that aluminium block. We need something to measure temperature with. What is the piece of equipment which we use to measure temperature in physics? Say your answer to the video. It's a thermometer. So we need to draw a thermometer inside the metal block. Again, doesn't need to be a good diagram. We just need to label it clearly. So I'm labeling it thermometer. We also need to have the heating element inside the metal block. So here is my heating element, which I will label heating element. But that needs to be connected to a power supply. So we need to have a power supply. Here's my power supply. Again, it doesn't need to be a good picture, but it needs to be labeled power supply. We need an ammeter inside that circuit. Let's take that back to the heating element. And we also need a voltmeter, and the voltmeter should be connected across the heating element, not across the power supply. Because if the voltmeter is connected across the power supply, it's going to measure the voltage across the power supply rather than the voltage across the heating element. Why might those be different? Say your answer to the video. So those voltages might be different because perhaps some of the voltage would be transferred across the wires, because wires do have resistance. So I'm going to connect a voltmeter across the heating element. So there we go. That's all the equipment that you need. You don't need to show the mass balance in this question. For part B, we need to actually describe how we would calculate specific heat capacity, what measurements we'd need to take, what exactly do we need to do. So the starting point here has to be the equation for specific heat capacity. What is the equation for specific heat capacity? Say your answer to the video now. The equation for specific heat capacity is energy equals mass times specific heat capacity times temperature change. Therefore, if we want to measure the specific heat capacity, it's a good idea to rearrange this equation so we can see what specific heat capacity depends on. Pause the video and rearrange the equation now to make C, the specific heat capacity, the subject. You should have got specific heat capacity equals energy divided by mass times temperature change. Now, we need to focus on each term in this equation and work out how we're practically going to measure it. What does E stand for? Energy. What does mass, sorry, I just told you the answer. What does M stand for? Mass. And what does theta stand for? Temperature change. So how are we going to measure M, the mass? We would measure it with a mass balance. How would we measure theta, the temperature change? We would need to use the thermometer before and after turning on the power supply. How are we going to measure the energy? So this is the tricky bit. and it needs us to use the equation energy equals power times time. But for the power, we need to use the electrical power equation, power equals current times potential difference. So let's write a description of what exactly we're going to do. So I'm going to do this as a step-by-step 1, 2, 3, 4, just to make it very clear. So step 1, we need to measure the mass of the aluminium block at the beginning. We do that at the beginning because the aluminium block is going to get hot and we don't want to hurt ourselves. So we measure the mass of the aluminium block on the mass balance. So first step, measure the mass of the aluminium, I'm just going to use the symbol Al, block with a mass balance. Now I'm not writing with proper grammar, just to save time. You should write with proper grammar in an exam, although in a physics exam you would not be marked down if your answer does make sense, even if the grammar is not perfect. So you would still get full marks, even if your grammar is not perfect, although you should still try and write with proper spelling and grammar. So measure the mass of the aluminium block with the mass balance. We then need to measure the starting temperature with the thermometer before we switch on the power supply. So we measure the starting temperature, I'm just going to write capital T, with the thermometer. Step 3 is we switch on the power supply, but we switch on a stopwatch at the same time. So switch on power supply and stopwatch at the same time. Step 4 is we now leave it on for however long we want. I would suggest 10 minutes, which is 600 seconds. So leave the power supply, which is connected to the heating element, on for 10 minutes. Then switch off. Now, at the point that we switch it off, we do have to leave the equipment for a little bit. We don't read the thermometer immediately, because what happens is still some heat is transferred to the aluminium block. So even when we switch off the power supply, there will still be some heat transferred to the aluminium block because the heating element is still warm. So what we do is we switch the power off and then we keep our eye on the thermometer and we note down the highest temperature it gets to. So we leave the power on for 10 minutes, then switch off. Step 5, write down the highest temperature the thermometer shows. I'm now going to move to the left, so 0.6. So now that we've done that, we are in a position to start doing our calculation. One thing is, while the power was actually on, we should have noted down the current and voltage. So leave power, so I'm going to go back to step 4. So where it says leave power on for 10 minutes, then switch off, I'm also going to write down, note down the current from the ammeter. I'm using I for current because that's what we use in electricity. And the potential difference from the voltmeter. Sorry about going really small there. So for part 6 now, we can work out everything that we need for the formula. So for theta, that's the temperature change. So that will be the final temperature minus the initial temperature, both of which we measured. M will be the mass from the mass balance. So whatever that was at the beginning, make sure that's measured in what units? What unit should mass be measured in? You should have said kilograms. And for the energy, I said we need to do power times time, where power was what? What did I say the electrical equation for power was? Yep, if you look on the right of the screen, you can see that power is current times voltage. So we do current times voltage times time. I just want to check that you know your units. What are the units for energy? The answer is joules. What are the units for power? The answer is watts. What are the units for current? The answer is amps. What are the units for potential difference? The answer is volts. And what are the units for time? The answer is seconds. Now we have a value for theta, we have a value for mass, we have a value for energy. Just one question before we then move on to part C. I said leave on the power for 10 minutes. So what will I actually need to put for my time in this question? If it was 10 minutes, say your answer to the video now. So I wouldn't put in the number 10, I would have to put in 600 seconds because there are 600 seconds in 10 minutes, and seconds are the units of time in physics. And then once I've done that, I've got everything I need. I would then, step 7, I would use the equation C equals E over m theta, putting in all of those numbers, and I would get my value for the specific heat capacity. You should also add the safety point that you should be careful not to touch the aluminium block once it's been heated. So whenever you're answering a question like this, an experimental question, get into the habit of saying what the safety points are. Now, there is one extra thing I didn't include, which I should have done. So around the aluminium block, there should be something that I've not put in the diagram. What do you think I should be putting around the aluminium block? Say your answer to the video now. So the answer is I should be putting some kind of insulation around the aluminium block. Why should I put insulation around the aluminium block? Say your answer to the video now. So the reason why I need to put insulation around the aluminium block is because I want to make sure that E in the formula is actually the energy which has been transferred to the aluminium block. If I've left my power supply on for 10 minutes, it's going to provide this amount of energy. I'm trying to work out the specific heat capacity of the aluminium block. If I use that value for energy, but actually some of the energy got wasted by being transferred to the surroundings, it's not the right value of energy. So we do need to put insulation around the aluminium block to make sure that we reduce the amount of energy transferred to the surroundings as heat. What's the word for heat transfer to the surroundings? The word we use is dissipation. Finally, question C. Methods used to determine the specific heat capacity may give a greater value than the actual value. Explain why. So this is to do with what we've just said. So what we've just said is even with insulation, some heat will still be transferred to the surroundings. It's impossible to fully stop heat being transferred to the surroundings. So therefore, when we use the formula C equals E over m theta to work out the specific heat capacity, our energy, which is transferred to the surroundings, might actually, well, if there is energy transferred to the surroundings, there will therefore be less energy transferred to the block than the power supply is supplying. So when we put our value into there, the value that we're putting into there is the energy supplied by the power supply. But the temperature change here is a temperature change due to the energy actually supplied to the block. Now, if those values are exactly the same because the insulation was perfect, then fine. But if the insulation was not perfect, which of those is going to be bigger? The energy supplied by the power supply or the energy supplied to the block? Say your answer now. So if the insulation isn't perfect, then the energy supplied by the power supply is going to be bigger than the energy supplied to the block. So therefore, the temperature change that the block experiences is going to be less than it would be if all the energy from the power supply went to the block. So again, I'm going to say that again. The temperature change that we get in reality is going to be smaller than the temperature change would have been if all the energy from the power supply went to the aluminium block. So because some of the energy has been lost due to dissipation, due to thermal energy being wasted, that means the temperature change is smaller than it would have been. Now, if this number on the bottom is smaller than it should have been, and if you look, you can see that C is inversely proportional to theta. That means if theta is smaller, C is going to be bigger. So in conclusion, because we actually get a smaller temperature change than we should due to dissipation, that means the value that we get when we measure the specific heat capacity is higher than it actually is in reality. Notice in the question it says the word explain why. What does that mean when physics questions say explain why? When physics questions say explain why, it means don't just describe what you see, don't just tell me about what's going on. I need a physics, well, I'm not going to use the word explanation to explain what explain means, but explain why it means you need to talk about the physics. You need to go into detail about the physics, which is why I've talked about the energy supplied by the power supply compared to the energy supplied to the block, which is why I've mentioned dissipation. So use lots of physics language when you're being asked to explain why. So that was a nice question about the specific heat capacity practical. We're now going to move to this question here. Please read the question. If you've not done it before, try it, do it completely, pause the video while you do that, and press play once you're ready to go through it. Okay, so the first question, part A, asks which energy resources should be used to meet the UK's commitment to the Paris Climate Agreement. Now, the whole point of the agreement is to reduce the amount of carbon dioxide. So only 2 of these energy resources do not emit carbon dioxide. Which are the 2 that don't emit carbon dioxide? Say your answer to the video. So the 2 that don't emit carbon dioxide are nuclear and wind. Then what you need to do is explain. So this word explain coming up again. So we're going to need to talk about physics again. And in this case, it's going to be talking about the specific advantages of nuclear and wind. So you should point out both of them, and it would be a good idea to say at least 2 advantages of each. So don't just say one advantage. Whenever you're talking about advantages and disadvantages of energy resources, talk about more than one. So do at least 2. If it's a whole discussion, for example, like a comparison, you should do at least 2 advantages and at least 2 disadvantages. Here, we're just talking about which ones should be used, so we're just going to talk about advantages. So please could you say 2 advantages of nuclear energy to your video now? So one advantage is that no carbon dioxide is released. That's the obvious one. It's non-renewable, so we can't do anything about that, but you get a very high amount of energy from a very, very small amount of fuel. So we say that nuclear fuel has a high energy density. That also reduces transport costs because you don't need to transfer as much fuel. Also, it's very, very, very reliable. Even though nuclear energy has a long startup time, it takes a long time to set up a nuclear power station and it's very expensive. Once you've set it up, nuclear energy is very, very, very reliable. Then we have to talk about wind, and we do the advantages of wind. So firstly, wind is renewable, which actually gives it an edge on nuclear power. It is unreliable though, so we can't put that as our advantage, and it does cost to build the wind turbines, but once you have built the wind turbines, there's no fuel costs because you don't have to pay for the wind. So there are no fuel costs. And just like with nuclear power, the main advantage, the main reason why we're using it is because there's no CO2 released. CO2 is a gas. It's got a special name, a something gas. What type of gas is CO2? It's a greenhouse gas. Coal and gas, these other 2 things mentioned on the table, are a certain type of fuel, a something fuel. What type of fuel are they? They're called fossil fuels. Okay, part B. Why would you still need fuel power stations even if you have enough wind in the UK? Well, firstly, even if you've got enough wind in the UK, it's not going to be all in the right place. It's not going to be all in the right place. So the wind won't necessarily be where the wind turbines are. So the wind won't necessarily be where the wind turbines are. Also, even if over a whole year, you have enough wind overall. Maybe you're going to get loads and loads of that wind in autumn and winter and not so much in spring and summer. The idea is that there could be days when there's no wind at all. And then there could be days when there's too much wind and you've got no way of storing that energy in between. So what we say is the wind is, what's the word we use for the fact that it's not always there? The word we use is unreliable. So wind is unreliable. Some days there won't be enough. So some days there will be not enough. And some days too much with no way to store. With no way to store the excess. Whereas with fuel, you get that reliable base load. So the idea is with wind, you may not always be able to supply the base load of what's needed. So with wind, you may not always be able to supply the base requirement. There'll be a certain amount of electricity which is needed by people in the UK. Finally, part C. So in the future, some European countries will only allow electric vehicles. How will this affect methods of electricity generation? Well, if everybody's using electric vehicles, that means we're not going to be using petrol and diesel as much, and therefore we're going to need to use electricity from power stations. So if we need to still stick to the Paris Climate Agreement, which electricity resources are going to need to be used more? Yeah, there's going to need to be a lot more nuclear and wind power. So these countries will need to generate more electricity. So they will need to generate more electricity. And it will have to be from nuclear and wind to comply to the climate agreement. So to comply with the Paris Agreement. Okay, the other kind of standard questions you get on this are comparisons between different energy resources. And I always recommend that you do at least 2 advantages and two disadvantages for each energy resource. Okay, the next question is a bit more mathematical. So read the question. If you've not done it before, please do it in its entirety. Pause the video while you do that, and then press play once you're ready to continue. So for part A, if the cyclist is riding along the road, they're using energy from the food that they've eaten. They have a chemical energy store inside them that is decreasing. So I'll actually write that on the line over here. So the chemical energy store decreases. The second part is interesting. It says the speed of the cyclist is constant when the work done by the cyclist is something the work done against air resistance. So work done means what? Well, work done means energy transfer. Now, if we want if the energy transfer by the cyclist was more than the work done against air resistance, what would be happening to the cyclist? Well, the kinetic energy of the cyclist would be increasing. The cyclist would be going faster. If the work done by the cyclist was equal to the work done against air resistance, that means there would be no transfer to kinetic energy and the cyclist would stay at constant speed. So the idea is that the speed of the cyclist would only increase if kinetic energy increases. For kinetic energy to increase, the work done by the cyclist would have to be bigger than the work done against air resistance. So the only way for the speed to stay constant is when the work done by the cyclist is equal to the work done against air resistance. Part B, the equation that links power, time, and work done. This is an equation that you should know off by heart. So what is the equation? The equation is power is work done against time. You can either do it in symbols or in words. I'm going to do it in symbols to save time. Let's just check that you know your units. What's the units of power? Watts. What's the units of work? Well, work means energy transfer, so it's joules. And what are the units of time in physics? It's seconds. Okay, moving on to part C. So we now need to actually work out work. So we're going to follow the usual method for solving equations. What's our usual method for solving equations? Hopefully you've said discus. So let's go through the steps. So for data, we've been given 200 watts. 200 watts is what physics quantity? It's power, so P is 200 watts. We've been told 1,800 seconds. What physics quantity is that? That's time. So our time is 1,800 seconds. We then have to write down the equation. So power is work done over time. We then substitute. So our power is, so your answer to the video. Yeah, our power is 200. What's our work done? Well, we don't know it yet, so we just leave it as W. And what's our time in this question? It's 1,800. We then need to rearrange our formula. So we do 200 times 1,800 to give us our work done. You can always use a calculator in physics. So when you type that into your calculator, you get an answer for work done of 360,000. What are the units? The units are joules. And what does the final S in discus stand for? Final S stands for significant figures. 360,000 would be an appropriate number of significant figures. It has two significant figures, and in our question we also have numbers with two significant figures. 1,800 has two significant figures, for example. So we've already got it as an appropriate number of significant figures. We don't need to do any rounding. Part D. So this is the tricky one that people sometimes struggle with. Calculate the percentage increase in the speed of the cyclist when it changes from something to something else. So the first thing to do is you actually need to say, well, when the power is 200 watts, what is the speed? And when the power is 300 watts, what is the speed? How are you going to do that? Say your answer to the video. Yep, you're going to do that by looking at the graph. Now, I'm just going to zoom into the graph so you can see it clearly. So I want you to find the speed when the power is 200 and the speed when the power is 300. Say your answer to the camera now. So hopefully you've said that when the power is 200, the speed is 9.5. When the power is 300, the speed is 11. It is just under 11, so if you said 10.9 or 10.8, that would be fine as well. But for the purpose of this video, I'm going to continue as a power of 300 being a speed of 11. So at 200 watts, the speed is 9.5 meters per second, and at 300 watts, the speed is 11 meters per second. Now I want the percentage increase. So to work out a percentage increase, you need to do the change in percentage. I'm going to use delta for change. So the change in percentage, not in percentage, the change in value divided by the original value. That's important. So you don't divide it by the final value, you divide it by the original value, and then times by 100 to turn it into a percentage. So what was the change in speed here between 9.5 and 11? What was the change in speed? Say your answer to the video. So the change in speed is 1.5 meters per second, because 11 minus 9.5 is 1.5. What was the original value of speed? Say your answer to the video. The original value was 9.5. You then times that by 100. You can always use the calculator in physics. So you do 1.5 divided by 9.5 times by 100. You get an answer of 15.7895%. Now that's definitely not an appropriate number of significant figures. You need to round it to a sensible amount. 2 would probably be the most sensible amount because 1.5 and 9.5 are both to 2. So 16% would be acceptable, but keeping a decimal place would also be acceptable. So you could also have 15.8%, but definitely don't leave lots and lots of significant figures. finally, part E, how does cycling uphill affect the maximum speed? So you might think it's obvious. Well, obviously the maximum speed is going to be lower, but you have to explain. See this word, explain again. So the idea is, if you're cycling uphill, you need to transfer extra energy, because what other energy store is increasing if you move uphill? The gravitational potential energy store increases. So the idea is, for 1 mark, you need to say that the cyclist's maximum power is still the same. So the cyclist can't suddenly have a bigger maximum power than they did before. They have the same maximum power. But now, when they go uphill, energy is transferred to GPE as well, to gravitational potential energy 2. Therefore, their maximum speed is lower. So notice the instruction words in the question. How? So when you get a how in a question, it means, does it increase, does it decrease, does it stay the same? So how does cycling uphill affect the maximum speed of the cyclist? For that, you need to answer, will the maximum speed increase or will the maximum speed decrease? So here the maximum speed will decrease. So that answers the how. And then the explain is talking about the physics. So that's where I've said the cyclist's maximum power is the same. What does power mean? Power means rate of transfer of energy, energy transferred per second. So the amount of energy transferred per second is the same, but more of that energy is now transferring to GPE. So less of it can be therefore transferred to kinetic energy of the cyclist. And therefore, the maximum speed of the cyclist is lower. Please have a read through this question. If you've not done the question before, do it now. Pause the video while you do it and press play once you're ready to go through it. Part A wants the gravitational potential energy formula. This is an equation you need to know off by heart. Gravitational potential energy is mass times gravitational field strength times height. What's the units for gravitational potential energy? Joules. What are the units for mass? Say your answer to the video. Kilograms. What are the units for gravitational field strength? Newtons per kilogram. And what are the units for height? Meters. Part B wants a change in gravitational potential energy. I'm going to use Descus, as always. The data, I know the mass is 50 kilograms. I know my gravitational field strength is 9.8. And I know that my change in height is 20. So I write down the equation, EP equals mgh. I substitute my numbers. So EP is 50 times 9.8 times 20. You can always use a calculator in physics. So 50 times 9.8 times 20 is 9,800. U stands for units. What are the units of gravitational potential energy? The units are joules. And significant figures, it's fine the way it is. Part C, 80% of the gravitational potential energy has been transferred to the student's kinetic energy store. So the first thing we do is we work out 80% of the gravitational potential energy. 80%, so that's 80 over 100 times 9,800. You could also do 0.8 times 9,800. Either of those methods works, and if you do 80% of 9,800, you get 7,840. So that means that the kinetic energy store is 7,840 joules. So that's your answer to part C. Part D, we need to use the kinetic energy formula. What is the kinetic energy equation? Say your answer to the video. The kinetic energy equation is kinetic energy is half times mass times velocity squared. We're trying to find the velocity, the speed. So we start by substituting. So we have 7,840 equals a half times the mass, which is 50, times the velocity squared. So that's the same as saying 7,840 equals a half times 50, that's 25, times velocity squared. What do you think we should do next? Say your answer to the video. We should divide both sides by 25 to get 313.6 equals v squared. What should we do next? Say your answer to the video. We should square root both sides to get that the speed is 17.7 meters per second. It does say, give your answer to two significant figures. 17.7 is how many significant figures? It's three significant figures. So we need to write it to two significant figures. What do you think 17.7 is to two significant figures? Say your answer to the video. To two significant figures, it's 18 meters per second. Finally, we have a question about a spring or a bungee cord. So for this question, we're going to need to use the ideas of elastic potential energy. So what is the equation for elastic potential energy? The equation for elastic potential energy is a half times spring constant times extension squared. Now, the energy stored by the stretch bungee cord is 24,500 joules, because I've changed kilojoules to joules. So 24,500 equals a half times the spring constant times the extension squared. So to find the extension, I need to consider the lowest part of the jump. So if we look back at the diagram, you can see that the lowest part of the jump is 55 meters from the bottom, from the top, and the unstretched length is 20 meters. So if the unstretched length is 20 meters and the lowest part of the jump is 55 meters, what do you think the extension is? Say your answer to the video now. So the extension is the change in length, which is 55 minus 20, which is 35. So I now have 24,500 equals a half times k times 35 squared. I'm going to multiply both sides by 2 to get rid of the half. So that gives me 49,000 equals k times 35 squared. And then I'm going to divide both sides by 35 squared. And that gives me an answer of 40 newtons per meter. This question is about efficiency. So firstly, read the question and have a go at it if you've not done it before. Pause the video while you do it and press play once you're ready. So this question is to do with efficiency. What's the equation for efficiency? Say your answer to the video. So the equation for efficiency can be given in terms of energy or in terms of power. Since this question is in terms of power, I'm going to do it in terms of power. So efficiency is the useful power output divided by the total power input. Now, when you're using this equation, it's very important that you use the efficiency in, so here's your choice. Do I use it as a percentage or as a decimal? Say your answer to the video. So when using this equation, we don't use efficiency in its percentage version, we use it as its decimal version. So if it's got an efficiency of 0.15, that's already as a decimal. The useful power output is what we don't know, so I'm going to just leave that as a useful. The total power input we do know, it's 3.2 kilowatts, which is 3,200 watts. Rearranging this equation, what do you think the useful energy is going to be? The useful power? So you should have said 0.15 times 3,200, which is 480 watts. How do we go from watts to kilowatts? Say your answer to the video now. You divide by 1,000, so the final answer is 0.48 kilowatts. Finally, question 12. Have a read of the question. If you've not done the question before, do it now. Pause the video while you do it and press play once you're ready. So part 1 here is a very common question when you have graphs of temperature against time. And you always get this kind of shape, which I'm going to highlight, where it's steeper at the beginning and less steep at the end. Steeper at the beginning and less steep at the end. And the answer to that is always the same. It's all to do with the temperature difference between the material and the surroundings. So just after the heater switches off, so at the start, so just after the heater switches off, the temperature, so the temperature difference, that's the key thing, the temperature difference between the water and the surroundings is highest. That's why the rate of change of temperature is also the highest. That's only 1 mark though. The second mark is for saying, therefore, the rate of energy transfer, is highest. So it's very, very common to get these kind of questions where you've got something cooling down and the rate of cooling is always highest at the start. The reason why is because the temperature difference between the thing that's cooling down and the surroundings is highest at the start. Finally, part 2 is a question about specific heat capacity. What is the equation for specific heat capacity? Say your answer to the video. The equation for specific heat capacity is energy equals mass times specific heat capacity times temperature change. Let's substitute. What should the energy be in this question? Say your answer to the video. You should have said 4,032,000 because in the question, you've been given energy in kilojoules. You need to change it to joules by timesing it by 1,000. The mass in this question is what you're trying to work out, so I'm going to leave that as M. The specific heat capacity you've been given, it's 4,200. What's the temperature change in this question? The temperature change in this question is 8. 58 minus 50. So I'm just going to do that multiplication of 4,200 times 8. You can always use a calculator. That gives me 33,600. How can I now find M? So I'm going to do 4,032,000 divided by 33,600 to give me M, which makes M 120 kilograms. If this has been useful, please like the video and subscribe to the channel to get more videos on Key Stage 3 Science and Maths, GCSE Physics, maybe Maths as well in the future, and A-Level Physics too.